Assalamualaikum warahmatullahi wabarakatuh. To the Honorable Dean of Faculty Mathematics and Natural Science, University of Jember, to the Honorable Associate Dean Academic School of Computing, Department of Physics, Sastra University, to the Honorable Associate Professor Swaminathan Venkatraman from Sastra University, to the Honorable Dr. Artoto Arsundato from Department of Physics, University of Jember, to the Honorable guest lecture participant and in this guest lecture today. Good afternoon, everyone. Welcome to the guest lecture on physics series. We are thrilled to have you all here and are looking forward to an enlightening session. To start our event, let us stand and join in singing Indonesian national anthem, Indonesia Raya, and followed by the hymn of University of Jember. Please, the participants to stand up. Thank you very much. Please be seated. And the next agenda is we have the honor of hearing welcoming speech from Professor Swaminathan Venkataraman from Sastra University. Please join me, Professor Swaminathan Venkataraman. The slide is yours. Thank you.
Thank you and good afternoon to all. It's my pleasure to be at University of Jimber. For this, I must thank our Vice Chancellor, Dean Planning and Development, Dean Sakshi, who had given me the wonderful opportunity to visit such a resourceful collaborator at Indonesia. And also I must thank Rector, Vice Rector, Professor Goen, Dean of Faculty of Mathematics and Natural Sciences, Dr. Dafik. It's a wonderful opportunity with which we will be having so many collaborative tasks, events, and in this collaborative work, today we are going to have a guest lecture in the physics. And in this juncture, I would like to thank Professor Ram Kumar, who has concerned to give the lecture on robotics. It will be followed by the lecture. Thank you very much. We are waiting for the events of this afternoon. Thank you.
Thank you, Professor Swaminathan Venkataraman, for your insightful remarks. And then the next agenda is I would like to invite the Dean of Faculty Mathematics and Natural University of Jimber to give the opening remarks. Please welcome Prof. David. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Today, it is very pleasure to welcome all of you to this guest lecture series. And this is a very important meeting because we can share our recent research, our knowledge to all of you. And for this special case, we invite the very distinguished guest from Sastra University, India, Professor Rangkuman Kanan, who already joined with this meeting. And also, previously, the visiting scholar from the same university, Sastra University, India, already been here in our campus FMIPA Universitas Jember, Dr. Swaminathan Venkataraman, who already effectively working with us in combinatorial research of interest. Hopefully, with this session, the two invited speakers as a guest lecturers in this meeting can give you a lot of an open idea to gain the research novelty in the short future, especially in the physics research topic. And also, we welcome all of you to give and to ask something to this guest lecturer, since it is very useful and important topic, especially in the leveraging artificial intelligence and machine learning in robotics side and also the other computer simulation. By reciting Basmala, I declare this session open for all of you. Thank you very much and enjoy this session. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor David, for the opening remarks. And the next agenda is we will review the webinar series, the guest lecture series, and there are two speakers. There is Dr. Ramkumar and Dr. Arthur Arvidato. After the presentation of the speaker, we will have a question and answer session. And then it is my great pleasure to introduce our distinguished guest speaker for today. Okay, the first speaker is Dr. Ramkumar Kanan. He is a renowned associate dean academic, School of Computing, Department of Physics, Juni University, with an extensive background in artificial intelligence algorithm of robotics. Today, he will be sharing valuable insights of artificial intelligence algorithm of robotics that a subject is of great significance to us all. Okay, without further ado, please join me welcoming Dr. Ramkumar Kanan. The time is yours.
Thank you, ma'am. So this is Ramkumar. Very glad to meet you all through online mode. And I would like to thank Professor Swaminathan for giving me this opportunity, for creating this link and giving this opportunity. Now I would like to share the screen and I will start my lecture.
Okay, you can start.
Whether my screen is visible?
Yes.
Yeah, fine. So the title of my today's presentation is about introducing the field of artificial intelligent algorithms implemented in the field of robotics. Okay, so that's my goal. So for another 30-40 minutes, I'll be presenting the slides. And afterwards, you can have queries or questions you can ask me. I will be in a position to clarify it. Okay, so we'll start our presentation first with the introduction of the outline of the presentation. So the outline of the presentation, I have planned my presentation something like this. First, I'll be introducing you to the field of autonomous mobile robots, wherein I'll be talking about wheeled robots. Okay, something, there will be wheels. Yeah, am I audible? Hello? Am I audible? Am I audible?
Yes, it's clear.
Yeah, fine, thank you. So I'll be introducing you to the field of autonomous mobile robots, wherein I'll be talking about wheeled robots first. Okay, there are 3 core problems associated with this kind of wheeled robots. And I'll be introducing you to the artificial intelligence based probabilistic reasoning algorithm, something called as Bayesian inference. And then I'll be introducing you to the idea of mobile robot localization as an estimation problem, how we can implement a localization problem, how we can solve it using this kind of probabilistic reasoning based AI algorithms. That's the focus of today's session. So let me start with the 3 problems in autonomous mobile robots. So the first problem for a mobile robot is where the robot is. Okay, the robot will not be knowing exactly where it is in terms of the environment. So for example, a robot, something like this, if it is going to be there, okay, you can see clearly it is a planar robot. It is moving in a plane. Okay, so if I allow the robot to move, you can see the robot is moving. So if I allow the robot to move, it will be moving like this in a wheeled robot. Okay, can you see it, everybody? So you can see that the robot is moving. Okay, it is moving in a 2-dimensional plane. Okay, so in order to know the pose of this robot, you require 3 information. One is the robot is moving along the, for example, along the X and Y direction. Can you see it? X direction, this is X direction, this is maybe Y direction, this is X direction. Okay, the X and Y direction informations are quite important for knowing the pose of the robot. Pose means what? Position and orientation. So in order to know the orientation of the robot, so I need to rotate. This robot can be in any orientation. It can be like this, or it can be like this, or it can be like this. Okay, so the orientation of the robot is also important to me, as well as the 2 X and Y directions are also important. So if somebody is going to ask the robot where you are, then the robot has to tell, I am at a particular X value, at a particular Y value with a particular theta value. That means X direction along 2-dimensional coordinate, Y direction along the 2-dimensional coordinate, theta, the orientation along the angle. Okay, the angle is also important, the orientation. So these are all something called as the where I am question. So in the robotics domain, they call this question as a state estimation problem. So a state estimation means what? The state of the robot is X, Y, and theta. So I am interested in knowing that. Okay, that's the first problem, the research problem. The field of the researchers in the field of robotics they work with. So in order to get that information, they use sensors. Okay, you can see in the first block. Can you see this block, the sensing block? The sensing blocks, in fact, the mobile robot will be equipped with sensors. Okay, the sensors can be LiDAR sensor, or it can be odometry sensors, or it can be a camera sensors. So using those information, the robot has to know where it is. So initially, the artificial intelligence algorithm that you are going to learn today is something called state estimation localization algorithm. So in order to understand this localization algorithm, you should be learning something called as probabilistic reasoning approach. Okay, so I'll be teaching you that. I'll be presenting that idea. So once the robot knows where it is exactly, then the next question is where it needs to go. Okay, so basically in a 2-dimensional space, okay, if it is this is a 2-dimensional space, the robot is here somewhere. Okay. Initially, the robot has to know in terms of the X, Y coordinates. Okay. So the robot has to know where it is. So this is the X value, this is the Y value. Along with that, you should also know where it is going. Yeah, somebody has said something. What is that? Any query? Okay. So the robot is the first state. This is the first state. It is going to the next state. So the where I am question is the first question. Where I am. Then the robot has to navigate in this 2-dimensional path. Okay, so for example, you'll be given a starting point here. This is your starting point, and then this will be your goal point, goal. So the robot has to plan a kind of trajectory. So this is called as path planning algorithms. Path planning. So basically, we can implement many AI-based search algorithms. AI-based search algorithms for planning this path. For example, the robot can move from this point to this point in many different ways. For example, it can go like this. It can reach from this point to this point like this, okay? Or otherwise, it can go something like this. Can go like this, and then it can go take a route like this. So there are multiple different ways in which a robot can reach this final state of 4. Okay, there are number of paths, trajectories available before the robot to move from the state 1 to state 4. So how does the robot knows, okay, from which particular path it has to choose? Okay, which particular path is optimal? This is called optimal path. So there are algorithms like AI-based search algorithms which a robot can use. So the robot can use AI-based search algorithm. Search means what? It will be searching for a particular optimal path. Okay. So then that is a problem. Then I also mentioned about the third problem, which in fact we call it as the how do I get there problem. In order to, after you plan your path, where I am going, that will be taken care by this path planner. And once the robot planned its path, it has to move on that particular path. So for that, you require a feedback signal. Okay, you should estimate the state, and then there is a trajectory you have planned. Okay, so you have a trajectory to track. So the robot is here. So the trajectory goes like this, and it will be reaching the goal point. The second state, the robot, if it goes somewhere over here, the robot has to be instructed that there is an error. Okay, there is an error in the trajectory. It is not tracking the trajectory. So the information has to be given to the wheels of the robot. Thereby, the robot will be moving towards the trajectory. This is a trajectory. It is called fundamentally a problem called control problem. In the field of engineering, they call it as control problem. A control problem means what? You have a desired trajectory to track. This is a desired trajectory, but the robot is moving now because of the inputs that you are giving to the wheels of the robot. Now the robot has deviated a bit from the trajectory. Now the robot has to be given control commands. Okay, the control commands means what? You'll be giving that commands to the wheels of the robot. Thereby, you are pushing the robot towards the desired trajectory, and thereby you'll be reaching your end goal at some point of time. This is called as robot control, they call it. Okay, robot control means what? You'll be giving the appropriate control signals to your actuators. The actuators are nothing but your motors connected with the wheels. Okay, so you can see here there are certain motors connected to this robot. So you can see here within this thing there is a right wheel, there is a left wheel, and then you can see in the right and left wheel there are left and right motors are there. Okay, that is why this particular thing is moving. This robot is moving. So naturally the robot wheels has to be controlled in order to meet out your requirements. Okay, so in that way, there are 3 important points that you should remember here. Number 1, the robot has to know where it is in terms of the environment. That you call it as a state estimation problem. Okay, the first problem, as I told you, first problem is state estimation problem. So here the state of the robot is nothing but the x coordinate, the y coordinate, and theta, the orientation. X, y, theta. This information, if you have it, the robot knows this information. The pose means what? Position. Position comes through x and y coordinate value, and the remaining thing is orientation. Orientation is the angle. Okay, the state estimation problem is the first problem. You can tackle it using intelligent algorithms, like AI-based algorithms. That's what we're going to see today. The second problem is called as a path planning problem. Once the robot knows where it is, then it has to move from one particular starting point to another destination point. There are number of paths that are available, trajectories that are available. Trajectory means this trajectory has to be identified using search algorithms. There are a lot of search algorithms. And the third problem is something called as control problem. Once you identify the trajectory, in the trajectory, the robot has to travel. So for that, you should give control commands to the actuators. The actuators are nothing but the wheel motors. They are the wheel motors. You are going to give inputs. So this wheel motors has to be actuated, so it will be traveling in the given path. For knowing the state, you should know some sensor information. The sensors can be encoders or LiDAR sensor. Okay, these sensors can provide the required information about the state of the robot as well as the orientation. So now with that background, now let us move on how to study the Bayesian based algorithms. Okay, when it comes to Bayesian rule, there is a mathematical approach. They call it as Bayes rule, where A1, A2, An be the disjoint events that form a partition of a sample space, and assume that P of probability of a particular event A is greater than 0 for all I. Then for any event B, such that probability of B greater than 0, we have the Bayesian formulation, something like this. Now let us try to understand this idea in terms of an example. There are two events that I have given over here. The event A is an aircraft present in the air, in the sky. Okay. Event B is the radar generates an alarm. Okay. So there are two events. So the first event can occur with a probability of 0.05. And the second event, which you call it as when there is a probability, when there is an aircraft flying in the air, the probability of the radar detecting is very, very high. So this is called as conditional probability. So to understand the conditional probability, what I have given over here is probability of aircraft flying in the air, that is the event A. When an aircraft flying in the sky, what is the probability of radar detecting it? The B event is the radar detecting it. What is the probability? What is A? Can somebody from the group tell what is A? What is the event A? Anybody from the group? A feedback from your end? What is event A? An aircraft flying in the sky. That is the event A. Okay. So what I am posing here, what is event B? Event B is a radar detecting that aircraft. Now what is probability of B given A is nothing but a conditional probability. A conditional probability. So you know that probability can lie between 0 to 1. So if I notice this probability is given as 0.99, I really mean that when there is an aircraft in the sky, the radar will detect it without any problem or with a very good probability of 0.99. Is the idea clear? Anybody would like to have some queries at this stage? Any query at this stage? You understand the two events? What are the two events? Aircraft is present. The B event is radar generates an alarm. Okay. So the probability of aircraft flying in the air is very low. The probability of B given A. Am I audible? Am I audible? Am I connected with you guys?
Yes, your voice
Okay.
is clear.
Okay, fine. Thank you. So now the aircraft probability of A complement B is nothing but when there is no aircraft, but still the radar is giving an alarm. It means it's a false alarm. That probability is extremely low. Now the problem posed through the Bayesian formulation is something like that. When there is an alarm, okay, when the radar is detecting something, I would like to know the probability of what is the probability of an aircraft present in the sky. So this is an inference problem they call it. Okay, so this inference problem is something like this. So when there is an alarm, okay, when there is an radar signal you are detecting, somebody is telling you that there is a radar signal, and you are now trying to infer what is the probability of aircraft flying in the air. So this is a very significant problem, an inference problem they call it. So through Bayesian approach, we can solve this problem. So Bayesian approach, Bayes theorem or Bayesian law is a very important algorithm in the probabilistic reasoning domain of under the AI technology. Probabilistic reasoning. So you are reasoning now. I am observing something, a radar signal. Based on this observation, can I now infer what is the probability of an aircraft flying in the air? Okay, this is a very important problem in the field of robotics also. Okay, so now, so that is computed with the help of the Bayesian formulation like this. Okay, the probability is 0.3426. Okay, so that's the probability computed. So now by using these algorithms, now we are going to solve the problem of the research problem of state estimation or robot localization problem. So let us try to understand it. So localization is now as an estimation problem is what I am posing here. So basically the robot is in a two-dimensional space. The robot must infer its pose from available data. The available data is noisy in nature because the sensors are all noisy. You will not be getting the right kind of information from the sensors. Basically, they are erroneous. Erroneous in the sense there will be a lot of errors in the sensor. Now you can see here the slide, the robot position is given by the two coordinate values, x and y, and the orientation is given by theta. So now I'm going to get a series of information about the system states along with the measurement data, which is going to come from the encoders and the accelerometers, and also some environmental measurements I'm going to get from the laser or LiDAR data or GPS or camera. So these are all going to provide me some information about the environmental information. And the last approach is I'm going to filter this information to get the pose of the robot, which I'm interested in knowing, which I'm right now interested in knowing. So the problem to be posed is something like this. So I have a robot, okay, which can be represented by the dynamics, Newtonian dynamics, okay, dy by dt is equal to some a times yt. This is the first order differential equation. So everybody will be quite aware of this, okay? So now the first order differential equation model can be built for this kind of robots, okay? So there are three information that I'm interested in. One is the state of the robot, the x coordinate, dx by dt, okay, how this is going to change, okay, with respect to the initial state, from this state to this state, a change in state, we call it. I'm interested in observing it, change in state, okay. So using a model, okay. So that model, I'll be calling it as state space model. State space model. Why it's called state space? I have three states here. In fact, if it is an xy coordinate, this is x, this is y. So any point you take in this space, that is going to tell something about the state. Okay, any point in this state. So I'm going to get a dx by dt value, a dy by dt value, and then I'll be getting d theta by dt value. So this is called as a velocity model. Okay, velocity model. I'm interested in getting this model. So this can be written in the form of a state space model, which can be written something like this. A capital X dot is going to be equal to some a coefficient times X plus I'm interested in giving some control signals U. So these are called as a state space model. Anybody from this group are aware of this kind of model before? Please say yes or no. Anybody? Aware of this kind of state space models? Have you heard of this term before? State space model? State information, state space model. Say yes or no, please. Please put it in the chat also. You are not. Are you aware of this model? Have you heard of this kind of model before? State space model. A differential equation model. Say yes or no. Please say yes or no. Please just type in the chat. Yeah, yes, a differential equation model, you are aware of it, okay? So naturally, I am interested in building a differential equation model for my autonomous robot. Why I am doing? Yeah. Because I need to track the state of the robot, okay? The state is the position and the orientation. Okay, I'm interested in tracking it. That's why I'm looking for that differential equation models. Okay, so now, so I will be telling you what is an estimation problem is. So once I know the kind of a model, something like this, okay, the differential equation, you know that, okay, if I differentiate the state like this, dx by dt, if I integrate it, what do I get? I'll get x back, the state back. So naturally, the state space model can be built like this. Okay, so the state, imagine this is your integrator. If I give x dot as input, I will get my state back. This is my integrator. And then I'll be using the coefficients of the differential equation model, something like this. So if I add this, what do I get? And then I'll be giving a B matrix and then a U signal, a control signal. And then I'll be passing it through a C matrix and I'll be getting the Y value. This is a measurement value. So this model, you call it as a state space model. So this is called x dot. If you look at this x dot, the state, the derivative of the state is equal to 8 times x plus bu. That is this part. You're adding. Okay, you're adding these two signals, you're getting this. And here, this is going to be y equal to c times x. There's a measurement. You are estimating the state and then you are measuring it also. Okay. So this model, you call it as a state space model. Normally, what we do is we'll be using a mathematical model. We'll be using a real-time system. And parallelly, you'll be running a mathematical model. A digital twin, they call it. So this model can be a state space model. And for the same control signal, you give it to the real system and to the mathematical model. Whatever output you are going to get, this is called as the error in estimation. So if this output and this output, if they are one and the same, it means your mathematical model is exactly capturing the dynamics of the real-time system. The real system dynamics is captured using your differential equation-based mathematical model. So this is called a state space model of the real system using the differential equation in terms of x dot equal to ax plus bu form and y equal to cx form. Okay, so get this idea clear in your mind. If you have doubts, please ask any doubt now. You understand this slide, what I am trying to convey to you? You have a real world robot. In the computer, you are also running a mathematical model. Now you are trying to find out you are giving the same control signal to both the real system as well as the mathematical model. Based on the error, if the error is negligible, it means your mathematical model is exactly matching with the real-time system. Okay, thereby you are in a position to estimate the system state for the given input signal. Are you getting this idea clear? If not, please ask me. I'll repeat again. Yeah. So now we are in the position of mobile robot localization. So now you can see there is a belief problem here. This mobile robot localization, you can see very clearly that there are two things. One is the prior belief of the robot at a time t. Okay. So the real world robot normally will have some errors. For example, if I ask my robot to go forward 1 meters, okay, by giving a control command U, it may reach exactly 1 meter, or it may reach 1.99 meter or 1.1 meter. Okay, so there will be some kind of uncertainty in the real world. Uncertainty means what? You cannot exactly tell where the robot is. Okay, give the control command exactly 1 meter to move forward. It may reach 1 meter, or it may reach 1.1 meter, or it may reach 0.99 meter also. So there is an element of uncertainty. So you need to model this kind of uncertainty using probability. So that is called as a probability distribution function. Normally you will be using normal distribution, a Gaussian distribution, something like this, for exactly modeling the behavior of the robot. That's where the probabilistic reasoning approach really comes into picture. So now you look at this. There are two equations given over here. Try to understand this. The first one is the prior belief of the robot at time t. It means based on the sensor data till time t minus 1 and the control commands what you have given to the robot till time t minus 1, what is the probability of robot being at a particular state? That belief, you call it as the prior belief. Now you have taken one more measurement from t minus 1 to t, and you are updating your belief about the state of the robot based on the control commands as well as the sensor signals. Now you have got a new belief about the robot state. So what is the point here? Now I've got two belief. Okay, the first one is the belief at time t minus 1. That you call it as the prior belief about what? The state of the robot, And now you go for a fresh measurement, a new measurement. Based on the new measurement, you are trying to revise your belief. You are revising or you are updating your belief. So now your prior belief will become posterior belief. So now you are adding some new information. That is why it is called revising the belief. Okay, once you revise the belief, you got a new probability. Okay, that is what this one. The belief at time t will be a new belief. Okay. So now there is a kind of two models you'll be using in the mobile robot localization. One you called as a robot motion model, which in fact using the state space model with the probabilistic sense. Okay, you have the control signals ut as well as XOR of t. Okay, so now this equation will become something like this. X dot will be equal to AX plus BU. Now this will become stochastic in nature. There will be a stochastic random noise you will be adding. What will happen? There is a control signal to the wheel. There is a state of the robot. You get a new X dot. Now this is no more deterministic. Because of the random noise, it will become probabilistic. The random noise is a distribution. Distribution in the sense, a normal distribution is what normally we will assume that for the noise. So naturally, this X dot is no more a deterministic sense. It is not deterministic. Not deterministic. It has become now a probabilistic. That is why your equation will become something like this. Now look at this equation. This is your robot motion model, which captures the dynamics of the system. You are at some initial state with a control signal, but you are seeing a probabilistic sense for the next state primarily because a robot can be anywhere in these dotted points. That means it is a distribution you are seeing over here. For the same control signal UT, it can be either here or here or here. Any point it can take. This is called robot motion model in a probabilistic sense, not deterministic sense. Likewise, the measurement model can also be the LiDAR sensor for a given robot state. The LiDAR sensor can also give different values. For example, a wall is nearby here. It can be here, it can be here, it can be here. Okay. So naturally, the robot will be sensing it. For example, the robot is right now here. With the help of a LiDAR data, it sends a LiDAR signal. A wall is over here. Exactly, for example, from this point to this point, let us imagine there is 70 centimeters, ideally. Okay, when the robot measures, initially it may tell 71. And again, when you measure, it may tell 69. And again, if you measure, it may tell 72. So there is an element of error in the measurement. This measurement error has to be accounted for. It has to be accounted. Accounted means what? You need to take into account. You cannot leave this error free. You cannot leave this error. Okay, somehow you have to probabilistically model this error. That's where the idea of normal distribution really comes into picture. For example, the mean value for this will have a high probability. For example, in this case, the mean value may be 70 centimeter, and 67 may be very low probability. 75 may have a very low probability. Okay, this is 75, this is 69. So you can see here the Gaussian distribution captures the error dynamics in the sensor. So that's what this data in fact indicates. The measurement model can capture this error. So using the Bayesian filter, okay, I'll be updating my belief with the help of my initial prior belief as well as the posterior belief, and I'll be getting new prediction, something like this. I'll be deploying both total probability theorem, okay, for computing the predictions of the Bayesian filter. So there are two steps involved in the Bayesian filter, which in fact is a Markov-based localization approach, an AI algorithm, Markov localization, AI algorithm. Very well explained in a book written by Tarun, book titled Probabilistic Robotics. You can refer to a free copy is available in the online. Okay, probabilistic robotics. Try to read the first chapter about the second chapter, chapter 2 on Markov localization, which talks about a model with a prior belief. Okay, using the probabilistic motion model. And that's given with an expression in equation like this. Okay, this is called as a prediction step. This is called prediction step. The robot is trying to predict its next state. Okay, imagine this. The robot is here for a given control signal U to the wheels of the robot for the given control signal. With the model, the robot is trying to predict where it can be in the next instant, where it can be in next instant. So imagine with the model, it's trying to predict somewhere around here it can be. With a Gaussian distribution, it can be somewhere around here with a mean and a variance like this. So this is achieved with the help of this expression. This is called a prediction step. Okay, so you can see here, the motion model is given over here. With the help of the motion model, it's trying to predict where the robot can be, XOR can be, okay, based on the control signal given at U of t minus 1, as well as the belief of the measurement data on the previous time step. Okay, so that is the first step. And then once having predicted, it's now going for a fresh measurement. Based on the measurement data, new measurement data, along with the motion model, okay, predicted at the previous step, built here. It is now trying to update the correcting the initial belief. Okay, that is what is called as a correction or measurement update. So this kind of models are being heavily been employed for mobile robot localization, and they are coming under two different categories. One you call it as a Gaussian filter, another one is you call it as a non-parametric filter. Under the Gaussian filter domain, you have three major algorithms. One is called as the extended Kalman filter algorithm. The other one you call it as the uncentered Kalman filter. The third one you call it as the extended information filter. Under the non-parametric approach, you have something called histogram filters and particle filters. Okay. So now let us try to understand what is the Kalman filter is all about. A Kalman filter is an optimal estimator that infers parameters of interest from indirect, inaccurate, and uncertain observation. It is recursive so that new measurements can be processed as they arrive. Basically, it can be applied for measurement noise which are of Gaussian in nature. If the noise is not Gaussian, then you will be going for different kind of other algorithms. Okay, even extended Kalman filters can be applied only with Gaussian algorithms. If it is Gaussian, if the noise is not Gaussian, then you have to go for different kind of estimators like Gauss-Markov or raw Blackwell algorithms. Basically, as I told you, the Kalman filter for mobile robot localization deploys a state space model, something like this. Okay, and the car model or the robot model is given something like this. Okay, so now with the real robot telling you something about the present state, the mathematical model will be telling you the new information about the same state. Now you need to fuse these two information in an optimal sense, thereby you'll be getting an optimal state estimation of the robot. So now you can see the predicted state estimate is given like this, the blue color one, and measurement update. By fusing these two information in an optimal sense, you are getting a new prediction x of k, something like this. So this is called as the state estimation algorithm. So what I'm trying to convey to you is something like this. Using a prediction model, you have an estimate about the state of the robot. Which in this case is x, y, theta. I have an estimate about this using my prediction model. Now, in the real world, there are a lot of uncertainties. Uncertainties means errors in the measurement. So you don't have an exact knowledge about the present pose of the robot. What you have is a distribution. Now I would like to update this belief with a new measurement data. So the new measurement is going to give, the measurement model is going to give another estimate about the same state. It's also going to be a normally distributed. Another estimate about state, but a new estimate. Now I got two information about the same state. Can somebody tell what are the two informations I got about the same state of the robot? What two informations I'm talking about here? First information comes from what? The first information comes from anybody from the group? You can type it. The first information comes from what? The prediction model. Okay, from the mathematical model, you get the first information about the state of the robot. From where you get the second information? Can somebody type it on the chat board? From where you get the second information about the state of the robot x, y, theta? From the measurement model. So now you got two information. So the most important, there is a chatbot question. In fact, you can type your questions in the chatbot. I'm interested in answering it. That there are two important problems. In fact, I told you the key research areas that are happening in the field of robotics is number one is the probabilistic robotics domain. Right now, I am teaching that probabilistic robotics, wherein you are interested in solving problems like state estimation problems. You'll be using sensors, for example, camera. Then you are entering into a domain called computer vision computer vision. And using this camera information, you are interested in doing something called visual SLAM problem. So I would like to talk about this a bit. Visual SLAM means what? Visual means using camera. So SLAM means simultaneous localization. I'm talking about robot localization here, plus mapping the environment problem. Simultaneous localization and mapping the environment. For example, the robot is here. It is seeing some obstacles over here. Okay, some obstacles. The human being is walking over here. So the robot, with the help of a camera, it will be seeing this obstacle, this person over here, and it will try to map those information. Okay, map. In order to enhance the perception capability of the robot. Okay, so the mapping is one important area of research going on with the camera. Okay, simultaneously, you'll be localizing the robot within the map as well as mapping the environment, unexplored areas. So this is one problem. It's a really visual SLAM is the first research problem. Visual SLAM. Okay, there are a lot of universities, they are working on this. Carnegie Mellon University, USA. Then University of Sydney, Australia. You can refer to Peter Cork, University of Sydney. And then you can refer to ETH Zurich for their sites for getting more information about visual SLAM problem. The second problem is called the control problem. In the AI domain, they are using an algorithm called reinforcement learning algorithm. I teach these subjects at undergrad level at my university. Okay, reinforcement learning is an important area of research. Okay, control problem. And for computer vision, in order to perceive the world, the robot uses a lot of machine learning algorithms. Okay, particularly YOLO, you look only once. Okay, YOLO algorithms are being used for computer vision. And then for path planning research, again, you'll be using a lot of search algorithms, AI-based search algorithms. And also you have something called as, again, reinforcement learning for planning the path. Okay, so these are some of the key AI algorithms widely being deployed. Not only ML, you'll also be using reinforcement learning. Okay, along with that, core AI techniques like Kalman filters and all. Okay, so this is the Kalman filter idea. You can see here. You are fusing the information. So initially the robot is not, this is a very interesting problem in AI. The robot map is given to the robot. Okay, initially the robot is right now here and it is not observing anything. The probability of the robot being in any one of these states is all equal. Okay, you can see it here. All these probabilities are all same. But now when the robot starts seeing one pillar, okay, its belief is now going to increase. You can see now. The robot can be anywhere here, or it can be here, or three possible locations are now identified. Okay. Now, with one more action taken, and along with one more additional measurement update, the robot belief is now going to enhance something like this. You can see the probability is shooting up here. So this kind of belief update algorithms are quite popular when it comes to robot localization algorithm. Using Kalman filters and extruded Kalman filters, you can achieve this. There is a lot of mathematics involved. I need to derive these expressions, okay, in order to explain to you these ideas. I think if you are interested in interacting with me for another 10 minutes, I'm interested in interacting with you. You can type your questions in the chat box. Yeah, anybody? Any questions you have, queries about these algorithms? I will explain. You just type your questions on the, anything you would like to know about robotics and all. See, I am talking about a particular field of robotics called autonomous wheeled robots. Okay, you have different other kinds of robots like mobile manipulator robots, okay, which can be something like this. Something like this. You can see this kind of robot, they call it as manipulator robots, wherein you can move these robots. Okay. You can move this robot. You can move this robot anywhere. Okay. Any particular axis you want to move, you can move. Okay. So you need to, this can be used industrially, but here also there is a trajectory tracking problem. There is a control problem. Okay. All kinds of problem, whatever I said for mobile manipulators, it can be applied for this robot also. So you have different kinds of robots. You can see here. This is called humanoid robot. Okay. Movement of this robot can be also be adjusted. So you have something called as mobile manipulator robot with a manipulator placed over it. Okay, you can run this. Along with that, you have something called a quadcopter robot. A quadcopter, something like this. Okay, it will fly. Okay, so all kinds of robots are there. So whatever, whichever area you want, this is a software called a Copliosim software. Okay, you can refer to, it's a freely available software. So you can use for robotics. You can use open source softwares like Copliosim, freely downloadable, or otherwise you can use robot operating system. I think some of you are somewhat heard of this term, ROS they call it. Copliosim is a simulation software. You can simulate all kinds of physics in this software using differential equation models. Okay. Yeah, any query? Yeah. If there are no more queries, I'll stop now. Yeah.
Okay. Thank you very much for the nice presentation. There is a question, but we continue to the second speaker. After that, we have a question and answer session like that.
So I need to wait. I have another engagement by 12:45. I need to go for another meeting by 12:45. I have a meeting, another meeting by 12:45. I need to go. Yeah. If you have queries now, you can ask.
Okay.
Yeah.
Okay. We have questions from the chat here. There is from Dr. Akobo. There is very interesting presentation program. What is the most problem of artificial intelligence robotics research in current days? Thank you.
Yeah, I mentioned that. I have mentioned that here. Okay, there are three main problems, robotic research problems. One is the visual slam. You can refer to the Carnegie Mellon University or Sydney University of Australia, Peter Cork, ETS Zurich. This is one kind of research problem, visual slam. Another one is a control problem using ML techniques, machine learning technique like reinforcement learning. The third problem, hot research area is a computer vision applied for robotics using YOLO algorithms. And then path planning algorithms, a lot of search algorithms are there. A lot of research is happening in this domain. Reinforcement learning is another area of research. Is it okay?
It's okay. Thank you. Thank you very much,
Thank you.
Dr. Ram. And then there is one question again from the audience. To Muhammad Arif, please, you can unmute your microphone and you can ask directly to Mr. Dr. Ram.
Yes, Arif, please.
Yes,
Proceed.
very interesting, Prof. Ram. I just have one question.
Yeah.
You have a linear model for prediction model, and also you have linear model for
Yeah.
measurement
right.
model, right?
Exactly.
Okay. Yeah. So does it mean like your robot will move straight or will move like curve or something like that?
Yeah, it moves, in fact, in curve also. But the point is, the key point is the dynamics. Okay, the dynamics of the robot. You are
Yeah.
modeling it with the differential equation. Okay.
Yes.
Differential equation. And I am using a linear model.
Yeah.
Okay. Even it can take a curve. It is all right. Okay. If a linear model, I can always take a curve. Okay. The dynamics is something different from the path. The path can be non-linear. Okay. But
Yes.
the dynamics is linear. You understand? So naturally, sometimes if the model you want to take a kind of a non-linear model, then there are different kinds of other algorithms are there. The algorithm, what I have shown to you is a linear-based Kalman filter algorithm, a Bayesian algorithm. If you want to go for a non-linear model, then you can linearize that non-linear model under certain operating condition, and you can use something called extended Kalman filters.
Yeah,
That
the
is
problem
another
is
algorithm.
computation time, right? The
Yeah,
extended
computation
Kalman
time is
filter.
a problem. And also you can have other algorithms like particle filters and other algorithms are there, which can handle non-Gaussian noise also. You are right. Computationally, these are all quite complex. But now with the modern day NVIDIA-based processors, graphical processing units and all that are available, people are now with the cost also has come down. So people are now going towards applying this kind of complex algorithms for solving autonomous mobile robot problems. Okay. So you have any other question?
Okay, thank you so much, Professor.
Yeah, thank you.
Okay, thanks very much for your answer, Dr. Ram. And then the other questions, any questions for the other participants?
You can email me. I have already shared my email. If you have queries, please email me. I will answer those questions whenever I can. Okay.
Okay, thank you.
Thank you.
You can send your email in the chat, the room chat. I think.
Yeah, I'm typing now. Ramkumar dot is it clear? Ramkumar at eae.sastra.edu. Okay.
Okay, thank you very much, Dr. Ramkumar Kanan, for your insightful and inspiring presentation. Please.
I thank all the organizers. I thank all the organizers for giving me this opportunity. I thank Dr. Swaminathan also for giving me this link. Okay, thank you very much all. Okay, thank you.
Okay, maybe if you before if you have the other agenda, you can leave. But before that, I think we have to take a picture together in the group like that with all of the participants. Can you okay, the participants please open the cam. We have to take a picture together with Dr. Ramkumakanan and Dr. Atoto. Before Dr. Ramkumakanan has the other agenda, please open your camera. I'm sorry, Dr. Ramkumakanan, can you stop your chat screen?
Okay.
Okay, thank you.
You all right?
Okay. I will. Okay, I will from here. We can take a picture. Please. I will count here. 1, 2, 3. Smile again. 1, 2, 3. And then once again. 1, 2, 3. Okay. Thank you very much, Dr. Ramkumakanan, for inspiring presentation. If you have the other agenda, you can leave the room, or if you can join our lecture, you can join it. Thank you very much, and give applause to Dr. Ramkumakanan. Okay, and then we continue to the second presentation from Dr. Atoto Arsundato. Dr. Atoto Arsundato is a lecturer in the Department of Physics, University of Jember, with an extensive background in molecular dynamics. Today, he will sharing valuable insight on the molecular dynamics method for material research, case study in nuclear material. Please welcome Dr. Atoto Arsundato. The site is yours.
Okay, can I start?
Yes.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon, everyone. Especially to Professor Ram Kumar and Professor Swami. Good afternoon. Yeah, actually, I have visited India, especially at Bangalore, at year 2005. It is a very interesting place for me. Yeah. Okay. Before I start my presentation, I want to thanks to my colleagues, Dr. Ratna Dewi Sharifah, also Mrs. Weni, also Dr. Fuad, and also Dr. Reza, and so Mr. Rizky, who helped me to prepare my presentation today. Also, thanks to the others that I cannot say all here. Also, I want to thanks to the Dean of Faculty, Professor David, who allows me to speak in this moment. Thank you very much. Okay, now welcome to my presentation. Okay, my topic of research mostly about molecular dynamic simulation, and today I want to discuss about the nuclear material corrosion in the LFR, that is some nuclear reactor design, and then I want to divide my talks about four topics or 4 points. One is about what is the problem and issue in the nuclear material, and then second is how to research, and then the third is important research, and then what's next for my future research. Okay, for part one, what is the problem and issue in my in the nuclear material? We can see in this picture, this is a design of LFR. LFR is, it means lead cooled fast reactor. We can see the dimension of this design compared with the human, it's very big. And in the center of the LFR, there is a nuclear core, reactor core, and then outside of the core, it's the coolant. The coolant in this design, we use molten lead or also molten lead bismuth eutectic coolant. Why we design this LFR? Because now more than 40% this LFR has better efficiency compared to 30% in traditional reactor, the current reactor. And then also lead has a high thermal conductivity compare water that used in traditional reactor. So this lead actually is effective for heat transport from the fuel element to the coolant, and then, but the problem is even this design is very good for future reactor, but now still has disadvantage. The most challenging problem of LSR, there is a possible damage caused by corrosion. So liquid lead or liquid lead bismuth, liquid red bismuth actually attacks the steel to make corrosion, very high corrosion. So my job is how to reduce this corrosion. We can see from this picture, in the left picture, this is IC steels in the interact with liquid lead at about 900 degrees Celsius, and then we see there is a very high corrosion here. There is a structural damage, and then if we use some inhibitor agent, currently we use oxygen to reduce the corrosion, and then after treatment of oxygen injection with some concentration, actually we can reduce the corrosion. You can see in the right picture like this. So we have two strategies to mitigate corrosion of steel. Usually we have three strategy. One is we have to find new steel material, and then second we have to find new coolant material, and the last we have to find new corrosion inhibitor. Okay. To do this research, actually we have two choice. We can investigate which experiment method or approach. We can also use a theoretical or computational approach. And in my research, we use MD molecular dynamics. What can we do with computational approach? One is actually we can predict the ideal concentration and composition of steel or ceramic material for future potential applications. And the second, with computational methods, we can estimate the ideal concentration or composition of new promising coolant. Yeah. Now we use lead bismuth. In the future, we can use we can find another coolant, maybe lithium or something. And then the third, we can predict new corrosion inhibitor agents. Now we can use oxygen, but maybe at the time we can use nitrogen or other. So so the point is how to reduce the corrosion in LFR. Now we talk about the MD program, molecular dynamic program. In my research, I used two programs, MOLDI program that created by Professor Peterson, and then sometimes I use LAMS that created by Professor Steve Plimpton and friends. Yeah. And why I use this quote, because I feel this two quotes is very good for research about solid and liquid matter, like in the corrosion of steel in the liquid like this one. That is why I use this two quote, moldy and lump. Okay, now we we continue to the second part of my research, how to do research. To now to learn about the corrosion, actually I see the corrosion is actually it's like a diffusion process. So some atoms move to another environment. So in the case of corrosion, we will see some atom in the surface of the steel cool to liquid like this mud, and then this make the steel damage. For molecular dynamic simulation, we can see this corrosion by calculating what we call MSD, mean square displacement. Mean square displacement to learn about the diffusion process, and then in the end of the simulation, we can calculate diffusion coefficient. If diffusion coefficient of steel or iron lower, then the corrosion is lower. If our diffusion coefficient of iron atom is higher, and then also the corrosion. So in our research, our job is find method and material that the diffusion coefficient of iron or steel is lowest as possible. That is our strategy. Calculate diffusion coefficient of steel lowest as possible. In the mean square displacement, the formula is you can see in the monitor. The formula is like that, and then if we want to find new material in the future that resistant to corrosion, we can find we can choose the composition and concentration so that the steel has diffusion coefficient lowest as possible. Now, how to run molecular dynamic program? Generally, we need two inputs for simulation. One is input about potential energy that describing the atomic interaction of the material. We call VR, V parameter. This potential energy, actually, there is many potential energy function. Reduction potential, Morse potential, AEM potential, ANM potential, etc. So between two different atoms, there is some atomic interaction potential. We have to choose this potential that give calculation accurate, how accurate the potential is can affect how accurate the calculation. Our physical physical value. Also, we need the simulant need the control of simulation, control of the simulant like temperature, volume, and then also pressure, then number of atoms, etc. Also, we have to find, we have to determine what ensemble that we use in our simulation. NVT, NVT, NVE, etc. In our simulation, usually I use NVT and also NVT ensemble to simulate the corrosion of steel in the like bismuth eutectic. So the point of this part is how we choose the atomic interaction potential to describe the material, the steel. Yeah. Also, we need input of atomic position before we start the simulation. We can use another code, let's say atom SK code. We can download this code freely from internet and then install in our computer. We can install in Linux, also Linux. Also, we can install in our Windows. Also, Macintosh. There is code that we can download free. Yeah. Okay. Now we continue to third part of my presentation, the important MD result. To do study of the corrosion, actually I need some experimental result for comparison of my simulation. It means before I do the simulation, I have to make sure my model of simulation, if we compare to experimental result, is accurate. In my simulation, in my research, I compare with Professor Zhang work that can be read from Journal of Nuclear Material. So based on this experimental result, I do my work to find some new steel, to find another inhibitor agent, to find some other coolant that have a good performance. This my first work. In my first important work is I have published at this journal, Nuclear Energy, in the years 2013, and I used Lennardson potential to. There is actually there is a first work, so maybe not so accurate, but can describe the phenomena very well. Oxygen can reduce corrosion very good if we use pure iron in the liquid line. We can see from this picture. This is before this picture before simulation. This is FCC iron crystal structure. Sorry, BCC, body center cubic crystal structure of iron before simulation. After simulation, there is a very high corrosion that caused by liquid lead, like that. If I put some small oxygen concentration, we can reduce the corrosion, and then the visual of crystal iron is more there is no high corrosion. If we add more oxygen, and then the structure of iron is very good, stable, and then if we add again small oxygen, and then this is the structure of the iron is very good, very stable, like there is no corrosion. But if we put more oxygen, and then the corrosion starting happen again, like this. So in this research, we have to find the oxygen concentration which the most value, most suitable value. Cannot small, but also cannot big. Okay. We can hear from this graph, there is only a small area where we can inject oxygen in the liquid lead coolant in the okay. So the point is the concentration of oxygen in the inhibitor must has a value of sufficient small, cannot too small, but cannot too high. Okay. And the second research of my work is I put iron in the liquid PBI. Lead bismuth eutectic coolant. Yeah. I have published in the Turkish Journal of Physics, and then the result is same like iron in the liquid lead. There is certain oxygen concentration for this case. Okay. And then my third research is about steel, iron, nickel, chromium, and titanium, and I put in the center in the liquid lead. We can see here, if we only have iron without so there is a pure iron, not steel. The diffusion is very high, so the corrosion is very high. But if we put small nickel here, the diffusion coefficient is too slow, to lower value. So this means low corrosion. If we put again another atom, chromium, the corrosion go down again, and then if we put the titanium atom, so the corrosion is very low. So in my research, we can find a new steel. We can see here Iron has 75% weight of all. So weight percent. So nickel around 10, chromium around 14, and then titanium and very small, 0 point, around 0.5. This is let's say maybe this is a promising field for use in LFR design. I published my research in Eureka Journal in 2022, and then in my another research, I am not to find new material, but I want to find new formula for accurate calculation. I want to find some atomic interaction potential function that support to material for accurate calculation of coefficient diffusion coefficient. This is my new formula, and then I use Lennardson potential type, and then we can see from this picture. Number 8 is my formula. Compare with experimental result, and compare with another formula. My formula is very accurate. Only has discrepancy or error about 0.40% compared with experiment. Compared to another formula that has a discrepancy about 50%. It's very big, and then our formula is very good result. Now we discuss the last part of my presentation. What's next of my research? As I talked about the material for accurate calculation, actually we did some atomic interaction potential function. The calculations depend on the accurate calculation also depend on the potential that we use in empty simulation. Usually, Lennardson doesn't recommend it to be used for metal. So that now I want to in the future I want to determine the potential that is artificial neural network ANN potential for my future material calculation. And this ANN potential needs a quantum mechanical theory to prepare the needed data. So that is my future plan. Okay, I think that's all my presentation today. Terima kasih, thank you, Nandri in the Tamil Nadu language, and I hope my presentation useful for all of you, and please, if there is question, I will be happy to answer that. Thank you very much.
Okay, thank you very much, Dr. Abdullah, for the providing information. Okay, we have a question and answer session. There is question from participants in the WhatsApp in the Zoom. I have clicked it from Evo Italia. The question is, what are the advantages and limitations of using the molecular dynamic method in the study of nuclear material? And how can this method improve our understanding of material behavior under extreme conditions such as high radiation and temperature? Okay, thank you. Please, Mr. Akasa to end the presentation.
For the question. Okay. The limitation. Yeah. Okay. I can read in the chat the advantage of molecular dynamic method. Yeah. The advantage is yeah, we can predict everything. We can predict everything that we can imagine. Yeah. We can predict the physical and chemical properties for many phenomena. Yeah. Which is the advantage. Because our tool on the computer, we don't need some real material, just the model. Yeah, that is the advantage. But the limitation is one that I said just now. The limitation is one is do we have accurate in atomic interaction potential? Because in the MD simulation, the different potential type can result can reduce the different result. So for every phenomena, we have to find the best potential for this phenomena. Let's say in my research, if only describe the corrosion, maybe it is enough if we use Lennart's potential. But if we compute certain physical properties, maybe this is not enough. We have to use maybe AAM potential or other. That this is the first limitation. Second is we cannot depend on our computer that we have. We cannot do MD simulation with many atoms. Yeah. Whereas in MD simulation, in MD method, molecular dynamic method, if we use more atoms, many atoms, this will generally produce accurate calculation. But our computer is maybe RAM, maybe storage cannot be this is not not enough for save our result. And so this depend on our computer. This is a second simulation, second limitation. And then the third limitation is, I think, for the good result that compared with experimental should be we have very good computer facility, maybe cluster, maybe supercomputer like that. For good simulation, we need support of good computer facility. Yeah, maybe like that. The limitation. And then improve. How can this method improve our understanding of material behavior under extreme condition? Yeah. In MD simulation, we can do simulation with different condition: extreme high temperature, extreme condition; high pressure, extreme condition, etc. So we can simulate, we can make a computer experiment for this extreme condition, and then after simulation we can see, we can check is it our material is stable or not, or how what we can do after the simulation, and like that. Okay. And then a question from, I think this is Dita. Does the resulting new equation have special condition to applicate it, and what about when the material under extreme condition? Yeah, new equation. Yeah, actually I propose for metal because actually Lenachun usually used for liquid and gas, not solid, metal solid, not metal solid. And then whereas my problem is still in liquid like coolant. So actually, if we use traditional Lenachun potential, maybe this is not so good. But I try to make some changing by changing the formula for mixing interaction between different atoms, and then as you see in my presentation just now, my solution is very good. So maybe for certain cases, for certain case, iron in liquid lead, maybe this is enough. But if we use for another case, maybe not enough, like that. Okay. Thank you very much.
Okay, thank you very much, Dr. Aswath, for this answer. And then there is one question again from the participant who has raised hand. Please, Mrs. Indra, you can give a question directly to Mr. Aswath. Okay, you can unmute your device. Thank you.
Okay, I think I'm becoming the presenter. Sorry, the participant who wants to ask one questions only. Pak Artoto, it still become my interested topic, favorite topic when studying the computations. I'm curious about how to inject oxygen atom in ion structure. Do you put the atom in irregular structure, irregular position, or you have to calculate in what position that oxygen have to be located, or maybe another method you can give short explanation, please?
Okay, thank you very much, Dr. Enda, for good question. Yeah. Okay, I understand what you asked. The oxygen actually, for MD simulation, for the starting point is we have to imagine the experiment, and then after that we mix a model based on the what's the experiment, what's the phenomena happen in the real life. Yeah. So in my simulation, I put the oxygen randomly in the coolant, not in the iron, in the coolant. I put randomly using random value, random value. We can use atom SK code to put this randomly in the coolant, but actually we can also use our Excel program. That is, I did in my PhD program. I use manually using Excel and then check the oxygen, the position, oxygen position in the randomly in the wet coolant using facility in the Excel random function, yeah, like that. But now in current day we can use atom SK code to put randomly this oxygen. Yeah. Okay, like that.
Okay. One feedback. Do you have ever tried to put or to locate the atom oxygen, for example, in a different position and study how it interacts or how the result from maybe the diffusion coefficient or another for the energy? Is it different or the same? If we put some atom in up or down on inside?
Yeah, for the case of oxygen in PB lab coolant, maybe this is same. But if we put another atom in the if we want to make a new steel, maybe iron nickel, we can put this nickel at the exact position and different position, and maybe the result is different. We can use atom SK code to put nickel inside in the iron bar in the certain position. You can do like that. You can do that with atom SK code. Okay.
Yes, thank you very much.
Thank you very much.
Okay, thank you very much for this question from the participants. And now we have finished our guest lecture with session today. As we conclude, let's give a final round of applause to Dr. Rangkuman Kanal and Dr. Arnoto Arsundanto for the presentation. And we hope you found the session as enlightening as we did. And please don't forget to fill the feedback from the academy in the present in the form. Just give the committee to the chat to the chat in group. And it is very important for us to improve our future events. So let's join us again in the next guest lecture series. And thank you very much for your attending and have a good day. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.